Kac-Moody. So that's another talk that I failed to properly prepare, but this time it's for a reason. So namely, it's hard, it's not clear to what I should talk about here. So well, it's easy to introduce the abelian category of Kac-Moody representation. That's not a problem, and that's what I'll do. But then one has to, but that's not enough for our purposes. Well, we have to work with the derived category. So again, let me just say there are notes. I wrote very extensive notes because I was expecting that this talk will be lacking in many respects. And yeah. So now we need to to define the derived category, and then it's a mess. So there's not a single source in literature that does it. And so, let me just say it. So there are two methods to do it. One can first method number one, which is developed in section 2 of these notes, you can bootstrap the category, so the definition from the abelian case. You have the abelian category, and so I explain the reasons why it's reasonable to expect that the category that you actually want is the derived category of the abelian category. As we know, if you have triangulated category with a T-structure, well, DJ category with T-structure is not at all true that the derived category of the abelian category will map in fully faithfully. In this case, we expect that it's we know it's the case on the bounded categories, and then you have to renormalize, do all kinds of awful things to get the category that you actually want. And so this is developed in section 2 of these notes. And well, it's not fully developed. I make a few steps and show you can actually proceed. And it's not nice. And it's the categories. This story is very brittle. So if you want to do something fancier, then you have to do it all over again. And again, basically, when you try to construct DG categories starting from an abelian category, you need to make sure that at each stage you work with objects as cyclic for your functors. You need to show that you can do everything on the chain level, and it's a pain. You need to, at every stage, either take injective resolution or projective resolution, and if you're applying, well, let's say 5 functors one after another, you have injectively resolve, projectively resolve, injectively resolve, and projectively resolve, and there is no end to it. Add one more construction, you have to, it's a nightmare. And then there is no alternative method. Basically, well, do it via int_co. And maybe what I'm trying to say is that, well, if you buy into the theory of higher categories, there is no representation theory. All of your representation theory must be formulated within algebraic geometry. So any kind of category representation you set up, it must be int_co quasi-co of something. Otherwise, it's impossible to develop it. And so this is the approach that I'll take. The problem is that, well, our Kac-Moody is of infinite type. And this adds another host of difficulties, which can be resolved, but I will not do it on the blackboard. So I'll show how the actual theory is constructed, but pretending that I'm in finite type. So this corresponds to sections 1 and 3 of the notes. Okay, so now I'll do section 1, which is the abelian theory. And there isn't much to say. Okay, what's Kac-Moody? So you start with a reductive Lie algebra G, and you fix kappa. It's a symmetric bilinear form. And first we'll do the case of a fixed point on the curve, and then you construct this Kac-Moody extension. I'll denote it x kappa, which is the central extension of the loop group, which is split as a vector space, and the bracket is given by the formula that you guys should all know. Something with the residue, I never remember what it is.
Everyone should know it but you.
Yeah. Okay, so this is the category, so this is the algebra. Well, and you see this algebra has a natural topology here. So I can also, choosing a coordinate, I can write it like this. So now let me introduce the category, the abelian category of modules. Okay, please forgive me. So until further notice, I'll be talking about the abelian categories. In the notes, I always put the heart here. And as you saw, my heart is not very beautiful. I'll omit writing it. I mean the abelian category until now. So just, OK. OK, what is it? So these are Lie algebra modules. Thank you for the suggestion. No. Okay. For superstitious reasons, I will.
Circle.
What?
Circle.
OK, whatever. But I mean the abelian category for now. So what are the modules? These are modules well, it's vector spaces acted on by Lie algebra with the following two conditions. The two conditions are very different. The first condition is continuity. So namely, you want this part to act continuously, which means that for every m in M, there exists a power n such that Tn gt, thought of as a subalgebra, kills what?
This kind of math I can understand.
Just give it a few minutes.
Just wait. And the second condition is kind of, well, it's the level condition. So here we have this element 1. So we want that this element 1 acts as identity. OK, so this is the category representations. Let me introduce a couple of objects here. So first of all, there's an object called the vacuum, x kappa. Well, it's induced from the trivial representation of g of Ox plus the center. So hom from vac into anything is invariant in this something with respect to g of Ox. So similarly, you can consider a bunch of other inductions. So some important modules are the Weil modules. So if called V lambda, well, it's same kind of thing. You induce but now you take V lambda, you take the lambda, say, stands for highest weight, you take V lambda to be the irreducible representation of G, and you make G of Ox act on it by evaluation. Take mod T. Can you still handle that? All right, and now there is more modules you can induce, but from deeper level. Some T. So, and again, it's home from it, you take vectors which are annihilated by the subalgebra. So these are kind of the basic representations. Why am I listing those? Because, well, if you set up the category correctly, these guys will generate. What? What's wrong? Okay, so this is, okay. Now, so that's actor number 1. Actor number 2 is the Kazhdan-Lustig category. It's the category that we actually want. Relationship between, okay, so let me call it Kazhdan-Lustig, G x kappa. At the level of abelian categories, it's and only abelian categories, this is a full subcategory. So at the derived level, you'll have the forgetful functor, but this forgetful functor will fail to be fully faithful. So the relationship between these two is kind of like all modules for the semi-simple algebra in category O. It's a very kind of precise analogy. So this is, let me call it in quotation marks, and I explain, G of Ox integrable modules. So what you want is that inside G of Ox sits inside the Kac-Moody, and so this is the Lie algebra of this algebraic group. So this is the full subcategory, again, at the abelian level, consisting of those M's on which the action of this Lie algebra integrates the action of the group. Let me say it again, even more kind of concretely. So M belongs to Kazhdan-Lustig G x kappa if the following conditions are satisfied. So this subalgebra acts locally and impotently. Which means that for every element m, there exists a power such that if you take power n, such that if you take n elements of this subalgebra, apply them to your element one after another, you'll get 0. Please distinguish it from this condition. Here I'm saying that for every m, there exists n large enough that it's this subalgebra kills. I'm saying something very, very different. I'm saying that n many elements of this subalgebra kill.
Just a second. Before you just said that on the Abelian level it will be fully fed.
Yeah,
then on the derived level
it will not be. Yes, but I'm not yet defining the derived category. I'm just defining the Abelian category.
But taking the derived category.
No, wait a second. Just forget the derived category. Just not now. Wait 10 minutes. Then it'll be derived stuff. Okay, that's condition number 1. And condition number 2, you can consider the constant g inside T of g must act locally finitely. Locally finitely. So if g is semi-simple, not reductive, you can combine the two in one by asking that just g of t acts locally finitely. So the equivalence between these conditions is explained very well in the original paper of Kazhdan and Lustig. So that's why the category is called in this way.
If g is not semi-simple, do you want to act locally finitely or?
Oh, sorry, locally integrably, sorry. Acts locally integrably. So the action of this finite dimensional G comes from an action of the algebraic reductive group G. All right, so
So this is saying it's Harishchandra.
these are exactly the Harishchandra. Okay, thank you for saying this. These are the Harishchandra modules. Okay, let me just say that. Just say these are. Just 1 second. So these are Harishchandra modules for this Harishchandra pair. Yes.
Can you just say what is written there on the bottom line?
I'm saying constant G acts locally integrably. So like as a representation of little g, it's a direct sum of representations of the algebraic group G, finite dimensional. Exact. Say again? I'm saying that if G is semi-simple, you can replace both conditions by 1 by saying that this G of t acts locally finitely. And read about this in the original papers of Kazhdan and Lustig. All right. Okay, so out of these examples, well, the vacuum belongs to the Kazhdan-Lustig category. These guys belong to the Kazhdan-Lustig category, but if you go to k greater than or equal than 1, these no longer belong to the Kazhdan-Lustig category. In fact, if you take k equals 1, this representation contains the copy of u of g inside.
Is this the subcategory there, or is
Full subcategory, abelianly. All right. Okay, so there are two more things to say about the abelian category. One is, and I think I'll skip one. I'll refer to the notes. So the claim is that, so there is a functor of localization called G at level kappa. It goes from Kazhdan-Lustig category at X at level kappa, consider D modules on bun G as we know it, but there is kappa twisted D modules. So, to explain this, I have to tell you what it means to be kappa twisted. I wrote it in the notes. Let me not do it. There are other things that I want to do instead. So just skip it. Not that I won't do it. I'll do it in the kind of fancy INCO language in one shot. I will not. There are some stupid formulas involved. We won't do any of that stuff when the machinery is set up properly.
say it for integral
part. I can say it for an integral kappa. I just don't want to. Again, read it in the notes. I just can't fit it. So another thing that
Maybe you could give a finite dimensional model.
I will.
No, wait.
No. I will. Again, time is limited. It's just that's the thing. Okay, there's one more thing I want to say about the integral level. Sorry, about the abelian category is the factorizable picture. So
it depends on the choice of a point.
Yeah. So well, it depends because the source category depends. So I should be properly saying.
I mean, you can identify them.
Yeah. So the source and the functor do depend on the choice of the point. So what I do want to say is kind of give a factorizable version. So I want to say how to construct what to do when your point is moving. And that, again, to simplify, I will do when there is no level. I just want to explain the kind of multi-point construction. So in what setting will I in what guise will I present it? So we fix the following. You fix the finite set I, and you fix, as in my talk yesterday, you fix an S point of x to the I deram, i.e. it's a map from S reduced to x to the I. So to such a thing, I will attach a category, an abelian category, so, well, which lives over the commutative ring A. It's an abelian category on which such that A maps to the center of this abelian category, well, in the naive sense, acts by endomorphisms on every object functorially. So let me describe this category. I denote it G hat xi modules. And similarly, it will be Kazhdan-Lustig G xi. Again, no level. I'm just setting level to 0 to simplify. Okay, so I want to first describe this Lie algebra, but that's after the tedious work we did yesterday. That won't be much doing. So namely, xi is just G tensor. Well, how to say? Okay, the algebra of functions on the formal puncture disk corresponding to xi. So we introduced this scheme, lived over S. No fighting in classroom. See, in my middle school, so like talking in class was offense number, well, I don't know which, I don't remember, okay, whatever. You know what I mean. Okay. I'm not far. I'm pretty close. So we had this scheme over. We have the scheme over X. Remember? So let me not remind you. It was this kind of scheme. Take a ring of functions and multiply by G, and inside you had, well, you had G, well, O dxi, non-punctured guy. And so both are Lie algebras.
What's central extension?
I set the level. I set level to 0. Again, I explain in the notes how to do the central extension. Just let me not do it. So these are Lie algebras. In the category of A modules. So we can consider the abelian category of A modules as an abelian symmetric monoidal category. Inside you can consider Lie algebras. So that's where they live. And you define modules again. So let me just define representations. Mod xi. These are A modules. Again, spec A is S. Modules endowed with an A-linear map, A-linear action of G hat, plus our continuity condition. And continuity condition is completely similar. Just one thing to notice is that, well, see, for every S and an S point of x to the I defined a Lie algebra let's say this one on S. And you can ask what happens. Is it a sheaf of Lie algebras on Xi de Rham? What do you think? Is it a quasi-coherent sheaf? Is it a quasi? So we know what the quasi-coherent sheaf is on any pre-stack. Take Xi de Rham. Is this assignment S goes to this a quasi-coherent sheaf on Xi de Rham? Yes or no?
I thought we couldn't speak.
Pardon?
I thought we couldn't speak.
Why not?
It's class.
No. Now you're asked. Raskin, is it a sheaf of algebras?
Sure, why not?
False. So the thing is that so if you have S prime mapping to S, you can take, well, which corresponds to the map of rings A to A prime. Well, you can do A prime tensor A with this guy, and it will map to the corresponding guy G hat X prime. So let me call X prime is the composition of Xi with F. You have a map like this, but this map fails to be an isomorphism. So it's not an isomorphism. Well, because here we have this process of completion involved. So this completion is not informed. Completions behave very badly against tensor products. So and it's one of the incarnations why kind of it'll be troublesome to set up the theory, because so again it's a sheaf of topological algebras in defining the category imposing this continuity condition, and you can imagine it will be a nightmare to do it derivedly, which it is. All right.
But can I explain what are you actually doing right now? So you define,
That's-
what is your goal? What is your kind of local goal?
I defined the abelian category. So see, my category of Kac-Moody is supposed to be factorizable.
Yes.
I defined the heart of that category.
You have already defined this Kac-Moody category. So now you,
At one point.
so you want to define factorization structure. Is
Well,
that,
in fact,
is this what you want to do?
yes. But
I mean, is this what you're doing now?
kind of. Let me just say it more precisely. So factorization category, it's for each I and for every S I'm supposed to give a category.
Yes.
I'm not giving that category, I'm giving the heart of its T structure. It's kind of a remnant.
An abelian category is factorizable.
There is no such thing. There is no notion of factorizable category in the abelian world. That's the point. Kind of.
Then why did you ask the question?
Pardon?
Why did you ask the question?
Who? He?
No, this.
No, I was kind of no. I did. It wasn't a factorizable question. I was asked like, just if you just take the sheaf of Lie algebras, will it be quasi-coherent as a sheaf of Lie algebras? I just asked for fun.
But over a point, have you defined it on the derived level?
No, and I won't, because I mean it's. I'll take a different path. So one way to define is that's what I said in the beginning. You can take the abelian category, take its derived category, tweak it a little bit, and that'll be it. And you can do it also for this.
If you take equivalent objects in the derived category of all modules, what would be the right answer?
Pardon me?
If you take the derived category, sort of infinity category of all continuous modules, and take equivalent objects there, is this the right answer?
Well, see, no. First of all, it won't be the right answer. Secondly, to make sense of this, you need to have G of O act on your infinity category.
Yes.
And that's a nightmare. Because the kind of action of a group in the category is a derived notion. Again, it's a section 2 of the notes. So what I want to do, I want to take a different route. So in taking this different route, I'll do Harishchandra modules, but as they should be done.
Can you take the formal completion of G of O inside G of O?
So that's what we'll be. Wait, that's what we'll do, but in the finite dimensional setting. I don't want to be fighting both problems at the same time. I don't want to currently be dealing with non-finite type issues. So here is our setting. We start with the, let's say, finite dimensional algebraic group G and a finite dimensional algebraic group H. So what I want to do, I want to properly set up the theory of GH modules, otherwise known as Harishchandra modules. So I'll give the definition. And as Kobe is suggesting, the primary object at play here will be the formal completion of G along H. And what is it? It's a group in scheme. And before I even do this, I will take H to be 1. So first, take H to be 1, and we'll be considering the most basic object, the completion of our group at the identity element. So whatever its representations are, we do want to see representations of the Lie algebra. So if you can set up the theory correctly, that must be a representation of the Lie algebra. And that's what we're going to see. So Raskin. It's okay.
Started it.
What? Yeah. Okay, so what we do, we consider B. Okay, when I write B, unlike the rest of the speakers, I do not. So for me, this is the pre-stack quotient. So this is
As opposed to what?
no sheafification. Yeah, I'm not trying to sheafify in the Tal topology any kind of topology. So like home from S to this guy is, how do you say it? Pardon?
Trivial.
It's what?
It's B of.
Yeah, it's the groupoid. So it's the groupoid with one object, and the group of automorphisms is, let me call it, point modulo hom S. In other words, this is a bundle. Oh, okay, it's just this. Okay, now this is a group object in the category groupoids, the quotient by it. All right, and this is a pre-stack, locally finite type. That did not exist in my middle school. And so I give the definition. So I define G modules to be int co of that. Okay, so now I'll try to explain two things. Why it's reasonable, why it reproduces Lie algebra modules as we know them, and secondly, why I take int co and quasi-co, why it's important to work with the int co here. All right. So
you define or you claim?
I define, I define, and then I'll claim.
The message is that you don't need to sheafify to define int co.
No, because int co functor satisfies descent, I don't need to sheafify to have the right category D modules. Okay, so let me try to say something about this category, and we'll see that it's on the nose spits out the category of modules of the Lie algebra as we know it.
Sorry, can you clarify just what's written on the blackboard?
Int co.
No, in the last one. So, well, B of.
So B of a group stack.
First, do you want BG to be equal to home, or you just. Do you want to erase this? What did you say?
Home from S to here.
The two first things are equal, right?
Ah. Okay, sorry.
Fine. Okay, so you're right. Okay, and now what is left?
So I'm saying what is B of a group pre-stack?
Yes.
It's the most naive thing possible.
So
It's B. Its values on a test scheme S is B of home from S to your group pre-stack. Home from S to B pre-stack is
I see.
it's a group in the category groupoids. You can take the quotient by it. Geometric realization, whatever.
Classifies the trivial bundle.
I don't want to say classifies the trivial bundle. What? One object and as many morphisms as there are elements of your group. Okay, and now it's int co. Int co, open parentheses, B, close parentheses. Okay. So I want to say that this category reproduces the category of Lie algebra modules as we know it. So consider the following morphism. Consider point mapping to our B. Call this map F. Now, so this map is what's called ind schematic. So the fibers of this map are ind schemes. And it's exactly the kind of morphisms along which we can take the direct image for int co. So int co is specifically adapted to taking direct images with respect to morphisms of the ind schematic. And moreover, it's ind proper. So it's the fibers take base change by an affine scheme, you'll get something which is a union of schemes which are proper, in fact, finite. So this gives you a pair of adjoint functors. It will be int co version, int co direct image, which will go from, well, int co of the point, which is vect, to, well, your int co of your classifying space. And moreover, so what you see, it's this monad. So this is the left adjoint. So this is, let me call it, let me write it here. So it will be, this is F int co lower star, and it's right adjoint upper shriek. So we have this adjunction because the morph is int proper. So and this defines a monad, and you can recover this category as modules for this monad. And if you compute what this monad is, namely, if you compute this, where is it? It's a monad that acts on the category vect. Well, how do you compute it? You make this base change. So, and here you'll see so you do this, which is the same as this, and you take int co direct image, and what you'll see, this is just tensor product with the universal developing algebra. So what you're using is the fact that distributions on the formal group is the universal developing algebra. So, well, that tells you that you're getting the right category. All right. Yes.
Distributions.
So what underlies this fact distributions is the following. You f up well, int co global sections. So let me say distributions on y, int co global sections on omega y. And if you take the formal group, you'll exactly see universal developing algebra. All right. So that's our Lie algebra.
Can you say again what?
So, sorry. Justin asked me, what do I mean by distributions? Distributions, by definition, is int co-global sections of the dualizing sheaf on Y. That's what defined to be distributions. All right. So now I want to define Harish-Chandra modules. What's wrong?
It's kind of weird. It makes sense for like a formal scheme.
But it's a formal scheme. Okay.
What compact objects are in this case?
In the category of modules for the Lie algebra? Excellent question. Excellent question. So anytime you have this, some kind of adjunction like this, where this functor is conservative and continuous, here is the description of the generating set of objects. Apply the left adjoint. Sorry, so we have this diagram. Okay, let me just say it. We have F lower star, int co-version, F upper shriek, going to our int co B, G, completion at 1. So as I'm saying, that it's equivalent to the following picture. This is U of G modules, where this functor is induction, and this functor is forgetful functor. So that's what this picture looks like. So if you want to compact generate, apply this left adjoint. And this is the functor of induction. So a typical compact object is U of G. And direct sums thereof. So like when you have this kind of adjunction, you immediately know who the compacts are, apply the left adjoint. And if the right adjoint is conservative, you know these compacts generate. I don't know what projectives are. We are in the DG setting. No, nothing projective anymore.
No, but when generic projective.
Yeah, but I kind of, I don't want to talk, yeah, sure. But I mean, I'm not talking about the T structure.
Still. So the image of your induction function.
That's cool. To shut up. Okay, happy? Yeah. Any more questions? So we haven't done much. We just set up the Lie algebra, but we knew it anyway, right? Kind of, why did we go through this trouble? You just take universal developing algebra, take modules. That's your category. But it gives something. So, but as in a second, we'll define Harishchandra modules, which are more painful to define directly. But
So this only applies. Your answer only applies to finite dimension model.
no, all. What do you mean?
Ah, okay, but so we didn't pass the question.
Finite dimensional G, which I'm doing only because I don't want to do int co in the infinite
Yeah,
type.
that's what I meant.
Finite dimensional G. Okay, so now so, pardon me? Completion. Why did it have to have a completion? I had a completion. So G hat. See, G completed at 1. Pardon? How do you complete U of G? Dual of the functions. So it's rather the dual of U of G is the function that you had. No completions. It's distributions in the formal group. So all good. Okay, so now I want to say the following. So we have this intuitive notion that, you know, a group acts on its own Lie algebra conjugation. So you expect, therefore, that the category of modules for the Lie algebra will be acted on by our group in Sam's sense. Sam yesterday, defined what it means for a group to act on a category. So I want to say that in this sense, our category of G modules is acted on by the group G. So let's do it. So what we have to do, I have to define a sheaf of categories. Let me call it, I'll call it G mod with a tilde. To distinguish from the category of G modules, it will be the sheaf of categories will be a sheaf of categories over what? Who knows? To have a G act on a category, you need to have a sheaf of categories over what? BG de Rham. All right. So to construct the sheaf of categories, let me do one more construction, which is, Sam didn't do it. He did it implicitly, but I'll do it slightly more explicitly now. So Sam said the following, that tautologically we have the pullback of sheaves of categories, but in fact we also have direct image. So if you have two pre-stacks y1 and y2, so I claim that if you have C1, it's a sheaf of categories over y1, I will define now its direct image, which will be a sheaf of categories over y2. Pardon me? What?
You want some one affinity.
No. Oh. No, the separation of direct image is always defined. So, namely, so let me say what does it mean to define the sheaf of categories? I have to define its sections of anything which maps to y2. So let me have S mapping to y2 by means of G. Let me say what is gamma over S of G upper star, F lower star of C1. Let me say what it is. Well, it's the following. You form your fiber product. So our morphism didn't have to be affine. So it's, again, some pre-stack. But let me call this map G prime. But I can always pull back my sheaf of categories by means of G prime. I'll get the sheaf of categories here. And now I'll take its global sections.
So if it's not compatible, is you vary S?
It is.
No.
Yeah.
No, because you're saying there's something to check. You have to check some tensor product means or something.
But it does, because see, okay, S prime to S, S quasi-co S prime is dualizable quasi-co of S modules, therefore it's commutable with the limits. So it is a sheaf of categories over Y2. Okay, such a nice construction. And we'll now perform it. Where am I? So we said we wanted a sheaf of categories on BG de Rham. Now I have this very nice map from BG to BG de Rham. Space maps to its own de Rham. And I'll take C to be, well, the following sheaf of categories BG, namely the most tautological one. I'll take quasi-co something. So again, it's not the category of quasi-coherent sheaves on BG, but rather the sheaf of categories this, which associates to every scheme mapping to BG quasi-co on that scheme. Call this map P and define G mod to be the direct image of this guy. Okay, I know it sounds abstract. Let's decipher it. So I've got, whatever happens, I've got a sheaf of categories on BG de Rham. Let's see what the sheaf of categories is.
Why didn't you take P of G completed? This also maps to BG, so you can compose.
No. Again, I want a sheaf of categories on this one.
Yeah, but you can compose and get a map from BG completed to BG to Rham.
That map is trivial. It maps to the point. BG completed is the kernel. But we'll see something like this. Okay. So, and I want to think of it, so want to think of G mod tilde as, well, incarnation of the action of G on G mod. Raskin, what do I have to check if I want to see that some sheaf of categories incarnates the action of my group on a given category? What's the first thing to check? I want to say that I claim that this guy incarnates my idea of the action of G on the group G on the category of modules of the Lie algebra.
I know this one. Pull back to the point.
Exactly. I want to see that the underlying category is what I want. Yeah? So want to see that sections over the point is G mod. That's what I want to see. Yes? Let's do it. How do I pull back to the point? How do I compute this? This is Rukavnikov. How do I compute this?
No idea.
Apply the definition.
Someone is saying it should be a fiber.
Okay, they are here. Okay, there are better students than you. Fratila, how do you? Okay.
You take your y2 to be BG.
Yeah.
Y1 to be BG. Y2 to be point.
Y2 to be, no, BG de Rham, right? It's like direct image onto BG de Rham. We're defining sheaf of categories in Y2.
Yes, so now you need to push forward to the point.
No, that's invariance.
Oh. Oh, so you pull back.
I want to evaluate on the point. So S is who? Okay, S is point. So point maps to BG deram. BG. What do we have here? What's the fiber product? Yeah, it's BG completed. So the sections of this is by definition int co. Oh, it was quasi-co. Okay, it's going to be. I forgot to say something actually. Okay. Quasi-co. And I wanted int co, so I'm in trouble. Okay. Okay, now I'll tell you a big secret. And I actually forgot to say why. I meant to explain, but I forgot to explain why we're actually dealing with int co rather than quasi-co. Well, remember, for any pre-stack y, we have this functor epsilon. So now, theorem, if y is a formally smooth int scheme, then epsilon y is an equivalence. So
formally smoothness.
Formally smooth is Grothendieck's definition that you can. Digression. It doesn't matter. So, okay, I'll tell you after. Formally smooth is in. Yeah, formally smooth means the following. You have A maps to A prime, surjection of rings with an nilpotent kernel. If you have a spec A prime point, you can always extend it to. That's formally smoothness. So you apply it to y equals this, and then using the geometric realization, you will see that this is an equivalence also for our BG hat. So in fact, quasi-co and int-co are equivalent in our case.
Why isn't it the psi does it? Why?
So psi, okay, I have to clarify. Psi and psi are the functors that only define for schemes. And then, so on the schemes you have psi and psi, and then when you go to arbitrary pre-stacks, so an arbitrary pre-stack, int-co is in no way a completion of any kind of quasi-co. See, the Gottno is this inverse limits. The only thing that survives for arbitrary pre-stacks is epsilon.
You should just say it's tensoring with the dual.
Oh yeah, it's yeah. I mean, we said it last time. It's tensoring with the dualizing.
Didn't you use the psi or psi to define the compactified Eisenstein series on the spectral side?
We're not doing anything. Wait.
You used the functors which you just said are not defined.
They are defined on schemes and Artin stacks. Anything which kind of smoothly equivalent to a scheme, you have psi and psi on that, but not in arbitrary pre-stacks, not on any kind of formal schemes. So this is an equivalence in our case. So I forgot. So therefore, well, quasi-co of our BG is in fact, but this functor is equivalent to int-co. So now you can ask, why did I bother talking about int-co rather than quasi-co? And the reason is the following. Yeah?
There you wrote y is the formal completion of G. There you wrote BG.
Exactly. So BG thank you for paying attention, is the geometric realization. So you can write it. You can write BG as a colimit of things that look like products of G's. For that reason, if the theorem is true for G and products thereof, it's also true for BG. So, what's your name?
Justin.
So Justin number 2 says that he says, okay, applied to y, well, we know it's equivalence for y. But now we do it for BG. Why is it the case? Well, BG can be written as a colimit of things that look like products. Okay, now let me come back, to the Lie algebra case and say, why did I bother about int-co? Why not work with the usual quasi-co? And the reason is the following. So let's go back to the same diagram. So we have this point mapping to BG hat. So what kind of natural functors? Okay, now let me write it int-co and quasi-co versions. Int-co. So there is f upper shriek to vect, and quasi-co in this case there's f upper star. It's equivalent, and this diagram commutes by means of upsilon. But in the case of upper shriek, this functor admitted a left adjoint. This is our int-co. And what I want to say is that in the quasi-co world, this operation of upper star does not typically, well, it admits a left adjoint just by virtue of this equivalence. The left adjoint to upper star, well, it's something very bizarre from the quasi-co point of view. So normally, f upper star admits a right adjoint, which is f lower star. And that's not at all what we want. We want a left adjoint. So this left adjoint is something very natural in the int-co world. It's something bizarre in the quasi-co world. And for that reason, we work with the int-co category. Well, this will give you a comonad. Well, it's okay, but this comonad consists of non-continuous functors. So this f lower star is discontinuous. It's not something, you can work with it, but it's not very convenient. See, it's direct image along an ind scheme. It involves it involves inverse limit. Yeah?
The category is modules over something. It's not comodules over.
Which category? This? Well, it is. Well.
It's a subcategory.
No, see. Well, exactly. So it's comodules for a comonad, but this comonad is not given by coalgebra. I mean, it's comodules for the following comonad. You take V to functions on this thing, completed tensor product. So as a manifestation, this functor is not continuous. So you don't want to work with this monad. It's kind of much more difficult to deal with. Well, yeah, you can take the function of the formal scheme and kind of tensor by V and complete. So this will be your comonad, and you don't want to work with it. It's much nicer to work with a monad, which is just tensor product with U of G. For that reason, we prefer to work with this monad, and that's why we prefer to stay in the world of int-co rather than quasi-co. Okay. So that was a detour. Now, okay, so we have our sheaf of categories G mod tilde. But now I want to take equivariant objects with respect to H. So we have H, a subgroup, and kind of this is what Sam wrote as G mod H. Objects in G mod equivariant with respect to H. And this is what we expect our Harishchandra modules to be.
Why do we need the whole sheaf of categories instead of just one?
Which one?
I mean, G mod.
Because, so the sheaf of categories encodes the action of G on Lie algebra representations. In particular, so that's what I'm doing now. I'm taking objects which are equivariant with respect to H.
Did you define the action of H?
No, but H sits inside of G. So if you have something over BG, you can pull it back to BH. And that will... BH de Rham. So again, Arkhipov, please, how do you compute this? So you have your sheaf of categories. So again, we want, so what is this by definition? And global sections, indeed. So it's BH de Rham. How do we compute such a thing? All right, let's do it. Let's do it. So we have BG de Rham. Sorry, BG maps to BG de Rham. Pardon? Yeah, so you have BH de Rham. You take the fiber product. What is this fiber product, by the way?
No, completion of
G along H.
G along H. But the RAM. No, with the RAM it's
Now I got confused. It should be this. Am I wrong?
But you have the RAM everywhere.
There's a B. Yeah, there's a B. Oh, okay, much better. Okay, so what do I have to do? So I have to. So sections of my thing here is by definition the same as sections of my thing here. So I have to take gamma. So gamma of my sheaf of categories, but what my sheaf of categories was quasi-co. So I'm supposed to say quasi-co on BGH. And that's kind of the answer we wanted. And again, I identified with int co by means of epsilon. So if you wish, I now give the definition of Harish-Chandra modules. Well, and it's what it should be. So GH modules is by definition int co of B of the following group in scheme, namely take the completion of H inside G. And that's that's the idea, right? Kind of you have the group acting and the rest of the directions are Lie algebraic. And now we reproduce this answer kind of algorithmically by taking H equivariant objects inside G modules. So this is kind of crash course on kind of algebra, geometric, how do you set up in algebraic geometry kind of your basic representation theoretic objects. Now, in the remaining, I don't know how many minutes, 1 minute. Okay, maybe I'll do it, and then I don't know what we'll do in the discussion, maybe nothing. I want to explain localization from this point of view. So here is the kind of setup for localization. So you have some scheme Y, and you also have the following. You have another scheme Z. Y may be a stack, such that H acts on Z, and such that Y is the stack theoretic quotient. But you have more acting on Z, namely you have the Lie algebra acting on Z, G, in a way compatible with H. Kind of you want to say that Harish-Chandra pair GH acts on Z. How do we say it? Braverman. Out. Kremnitzer, how do we say that Harish-Chandra pair GH acts on Z?
I can just say that the group.
Which group?
The completion of GH.
Great. Oh, that's your good student. Acts on Z. So that's our datum. So like H acts as a group and the rest acts as a Lie algebra. So what we want to say that in this case there is a localization functor.
When you take the quotient by that you get Y derived.
No. All I'm saying is that so far Y, just Y as a stack is Z mod H. I'm not saying anything deep. All I want to say is that in this case we'll have the localization functor from GH modules to Yeah. You start with the datum. In this case, the datum provides for you a functor like this. How do you write such a functor? Okay. So now let's write. Okay, that's the last thing I'm saying. So for Kac-Moody, you kind of do the same. So it's actually important, and it's kind of this balance and Bernstein localization is exactly this type of thing. It's important to understand. So how do we write this thing? So again, left-hand side is int co on what? B, G. The right-hand side is int co of what? Y the So I want my functor. Give me my functor. So Kobe, you wanted to say something. What's your proposal?
We have a map from Y mod, well, Z mod H, which is Y, maps to, well, it maps to B of H. So
It maps to B of H, right? Not quite to that. Sergey, you had the proposal.
Yes, so we have a stack quotient of Z by this.
All right, so we have Z mod
Yes.
So what kind of, okay, so we have this categories, but we have the, so we have, okay, so we have these three geometric objects, and we have Y the So purely the level of geometries, who maps to who? Okay, this maps to this because this is Z something modulo the group maps to point modulo the group. That's okay. Why does this map to this? Because what?
Because H is included.
Yeah, I say that the RAM of this is already Y the RAM. Kind of when you do the RAM, you kind of chuck away all the nilpotent directions. So like from the point of view the RAM, G hat H is the same as H. Okay, so call this map F, call this map G. What are your functors? Seriously. Okay, pull back. F. What's the second functor? Huh? Okay. Now, why is this defined? Why do you think you can take push forward along this map? What kind of map is it?
Because it's formally small.
No, that doesn't matter. So what kind of maps do you know? What kind of map are you allowed to take push forward with respect to? In schematic. Is this map in schematic? Let's see what the fibers are. So the catch here is this map is not in schematic. So the fibers not in schemes, they rather look like point modulo some Lie algebra action. But it's not in schematic, you can think you're in trouble, but instead we have another word. We have the word inf schematic. So it turns out that int co has more functoriality than you had suspected, and in fact you saw this. So in fact this inf schematicity already appears when you consider de Rham cohomology. If you consider de Rham cohomology, it's direct image from x de Rham to point, and this is not in schematic, and yet you can't take the direct image. Your direct image, int co direct image for this map is de Rham cohomology. So in this book in the making, we introduced the notion of inf scheme, and what is it? It's a pre-stack whose underlying reduced stack is a scheme, and the only condition that you need, so then you have this fluff of nilpotents in kind of DG directions, and you know what's happening with them. So the only condition that you need is that, so let me write this definition. So definition, a pre-stack everything of finite type is an inf scheme if, so Y reduced is a scheme, and the only condition you need is what's called Y admits deformation theory. Pardon me?
Oh, reduced.
Y reduced is a scheme, and the only condition is completely infinitesimal. So there's a notion.
Scheme.
What?
Scheme or in the scheme?
Scheme.
But it's
Reduced
reduced.
is scheme.
But still
You
have
are
an in the
applying
scheme.
No,
Can I have an in scheme?
yes, we call it in. Awkward as it is, we call them in schemes. Yes, affine Grassmannian is okay. But I don't need those guys now. I need underlying beat scheme, and then all you need is the notion of admitting deformation theory. And the claim is that this int code direct images are defined for morphisms that are inf schematic. If your base change by any affine scheme gives you an inf scheme. And basically, maybe that's the raison d'etre for int co. So this is, one sec. So this is what quasi-co does not allow you to do. So to have this kind of functoriality, well, that's kind of the full power of int co lives in. What? To admit deformation theory? Indeed. Okay, let's declare it formally over, and then I'll tell you what it means to admit deformation theory. So it's DAG 10 or whatever, but I'll tell you. It's infinitesimal conditional, cotangent bundle. So the claim is that this kind of, for obvious reasons, this is in schematic, and so this is well defined. All right. That'll be in question time. All right.
So,
Just say one word. Is the upper thing the incarnation of the Euro algebra?
Yeah. So yeah, it's incarnation algebroid. Basically, kind of when you're doing this, when you're computing this in schematic direct image, you're computing Lie algebra cohomology. And so because it's Lie algebra cohomology, it exactly means that kind of the directions are infinitesimally stacky. Yes, homology.
Is y equal to z mod h?
Y was z mod h, indeed. Ivan asked if y was z mod h.
Since she is not bidirectional, you have to go through this thing of intro.
Well, section 4, I wrote up how to set up the int-co theory in general. What we do, you reduce it to finite type. You're not trying to kind of do infinite type directly. Just kind of, it's a series reduction how to bring it to the familiar situation.
When you say in one word what's problematic, when you start trying to do Kac-Moody?
Nothing is problematic. You just have to set it up right. So you have to. So I don't want to. Again, it's exactly Kobe's question. I don't want to deal with infinite type directly. You have to show how to reduce it to finite type, and you can. All right. So let's have a 15 minutes break. Then we'll have just open question time.